Hello, Algebra 1 class. Today you're going to learn about the difference between correlation between two variables and a causal relationship between two variables. For this warm-up, I want you to look at each of these four situations and describe the strength of their relationship and the sign of the relationship. Like it is positive if they're both going in the same direction, both increasing. If one increases, the other increases. Or it's negative if one increases and the other decreases. And so for strength, I'm looking for you to decide if it's a strong relationship or a weak relationship. And in this point, when I'm talking about relationship, I'm just talking about correlation. Like, is the line of best fit that would fit this variables a strong correlation? Go ahead, pause the video and write down your answers, and then we will go over it. All right, let's discuss them. For the first one, it's the used car price and the original sale price of the car. And you would expect that a used car price is higher if it was a higher priced car to begin with. There's many other variables involved, but you would argue that this should be a strong positive relationship. The next one is used car price and the number of cup holders in the car. So, I don't know, maybe you could argue that the more cup holders, the more valuable the resale price of the car is, so you should be able to get more money for it. But most likely, the number of cup holders has very little to do with what the used car price will be. The next one, used car price and the number of oil changes the car had. So I wrote this as strong negative. You might argue that this was maybe a little bit weaker, but if it's had more oil changes, then that means it's been running longer, and the used car price should be lower because the car is even older. So that's why it's a strong relationship, but it's a negative relationship. Those variables are going in different directions. And the last one is used car price and number of miles the car has been driven. So if the car has been driven a lot of miles, that means it's had a lot more wear and tear, and the used car price should be lower. So that's why this one is a strong negative relationship. I want to look at just the last two here and ask if the used car price is directly caused by the number of oil changes the car has had or the number of miles the car has been driven. So that's kind of a little bit of a different question. There can be correlation, but is it truly caused by one variable to create the change in the other variable? And you could argue in both 3 and 4 that these two have a causal relationship in that the number of oil changes the car has had has a direct impact on the used car price, and that the number of miles that the car has been driven causes the used car price to change. In this activity, we're going to look at 4 different examples. So in each case, you're going to see a scatter plot, you're going to see a line of best fit. So you'll definitely see that all of these have correlation. What I want you to try and do is to write a sentence or two describing how you think the variables are related. So why they're related the way they are. Why don't you pause the video and try that on A and B, and then we're also going to talk about whether there's a causal relationship. Okay, go ahead and see what I wrote down. In graph A, what I see is that the more inches of rain you have, precipitation in inches, then the more percent of students are wearing jackets. And that makes a lot of sense. When it rains, more students will wear rain jackets to school. In B, we have the time in hours it takes to read a book and the number of pages. And I looked at it really the other way with the variables, but you would argue the longer the book that it is, or the more pages in the book, then yes, there's more pages, it takes longer to read. So these have both strong positive relationships. Now, the follow-up question is, are these causal relationships. And what I'm asking here is, does one variable cause the other variable to change? So let's look at the rain jackets. When it rains more, do you think you wore more rain jackets? The answer is yes. And the rain is what's causing more students to wear rain jackets, most likely. To determine causal relationships, you really have to think about the meaning of the variables and how they are impacting each other. In B, you might not say it takes more hours, like the more hours it takes to read a book, the more pages it is, but you definitely would say it the other way around. The more pages you have definitely will take longer to read the book. And so that is also a causal relationship. Let's look at two more examples on the next page. Go ahead and read over these and write down a sentence or two describing how they are related. Pause the video here. Okay, take a look at what I wrote down. So in scatterplot C, we have number of tickets left at a party and versus the noise level at the party. So what I thought about, if there's more tickets left, then fewer people went to the party, and then it would be quieter. And that's why it's a negative correlation. Definitely, there is a relationship between the variables in terms of they definitely go in opposite directions. In D, it says if a student's height in inches is greater, then they'll score better on a vocabulary test in, percentage score that they receive. And what I thought about here is taller kids are usually older, which means they've had more years of school and thus more vocab lessons. So they've done better on vocab tests. Okay, so now the question is, so we can definitely see correlation between these. The first one is negative, the second one is positive correlation, but are these causal relationships? And I would argue in both these cases, they are not causal. There's some additional variables that are causing the change. So the number of tickets left is not necessarily causing the noise level to go down. There could be many other factors involved in terms of who's there and maybe tickets weren't sold. There's definitely a relationship, but you can't argue that it's a causal relationship. Likewise in D, yes, taller children are usually older, and that means they'd have more years in school. What happens here is we have some additional variables, and there's probably a lot more factors going into why those vocab test scores also go up. So you cannot argue that these are direct causal relationships. Okay, this will help hopefully clarify what is a causal relationship. The key, it's not a long definition, a relationship is causal is one in which a change in one of the variables causes a change in the other variable. People often use the phrase correlation, not causation, or association, not causation, to refer to the situations in which there is a relationship, but it is not a causal relationship. A causal relationship means that a change in one of the variables actually causes a change in the other variable. So, how can we determine if there is a causal relationship between two variables? You really need to think about the context of the variables and the problem and determine if one variable's change is causing the other to change. One thing you can do is you can design an experiment that keeps one variable still and see if the change in the other does not occur, or try to isolate the variables. Let's look at two more examples. May states that the relationship between the number of miles driven in a taxi and the price of the taxi ride is a causal relationship. Do you agree with May? I do. This is a causal relationship. Think about it. The price of a taxi ride is directly related to the miles driven. There might be some fixed portion of that rate. So for very small traveling trips, maybe it doesn't matter. But the longer the trip, it costs more, more to run the car, and that's usually how their fee structure is driven. So the change of the length of the ride will change the price of the trip. In the second example, Jada states that the relationship between the size of a pasture and the number of cows kept at various farms is a causal relationship. Do you agree with Jada? I don't. Really, the number of cows kept at a farm is directly related to how many cows that the farmer wanted. Yeah, if they have a larger pasture, they could hold more cows, but they don't have to hold more cows. So you would argue that the size of the pasture and the number of cows, they might be correlated, and it might be a positive correlation, but it is not a causal relationship. Okay, for this activity, you're kind of on your own. I'd like you to try to pause the video and to find two variables that have a causal relationship, two variables that are strongly related, but where a third factor might be the cause for the changes in the variables. So one where it's not a causal relationship. And the third one is two variables that do not have a relationship at all. So they're not correlated at all. They're only weakly related. So the first one is a causal relationship. The next one is not a causal relationship, but correlated. And the last one is no correlation at all. Go ahead, pause the video and give it a try, and then I'll give you some examples that I found. Okay, take a look at my examples. The first one is the length of someone's foot and their shoe size. So you would definitely argue that the longer the foot, the larger the shoe size, and the reverse. So these are, it's a strong positive correlation, and it's definitely causal. The change in the length of the foot changes the shoe size. Okay, number 2, the amount of solar energy produced in a day and the number of people wearing sunglasses. First of all, I would argue that there's a strong positive correlation between these two variables. I would expect that the amount of solar energy produced in a day is higher on a sunnier day, and that also would be higher on a sunny day when the number of people wear sunglasses. Now, is this a causal relationship? The argument would be no. The number of people wearing sunglasses does not directly influence the amount of solar energy produced in a day. There's many other variables that are related that would cause that solar energy number to go up, in addition to the amount of sunshine. For number 3, this one is two variables that are really either weakly related or no correlation at all. And this is the number of hits by a baseball player in a game and the price of a tank of gas. So I don't know, maybe you could argue that the summer months when you have more baseball games going on, the price of gas is cheaper, but really there is no correlation or really no correlation in this case. So I'm hoping number 3 was very easy for you to find. Go ahead and make sure you found an example for each of these on your own that you feel good about. Okay, just to wrap things up, this summary is really nice because it gives you a bunch more of examples. So go ahead and we can kind of skim through it together. But let's jump through. Take a minute, read the first paragraph. All right. In the second paragraph, it kind of talks about a common mistake. People tend to make the idea that statistics think all relationships between variables are causal. And the key is your scatter plot and your line of best fit can only show a relationship between the two variables. It can't, and that they're both moving in the same direction or in opposite directions. But it can't determine if the change in one variable is impacting or causing the change in the other variable. You really need to understand the variables and the context of the problem and their relationship in order to make that determination. So this is a separate decision on whether the correlation is strong or not. So Another example is this one. Here it says the relationship, there's a strong positive relationship between the number of snowboard rentals and sales of hot chocolate during the months of September through January. So you would think when it's colder, you're going to have more snowboard rentals and more sales of hot chocolate. But it does not mean that an increase in snowboard rentals causes people to purchase more hot chocolate. So these are not, there's no causal relationship between these two variables. Nor does it mean that increased sales of hot chocolate cause people to rent snowboards more. So there's really probably a third variable, such as the temperature, that causes both variables to increase at the same time. Another example of one where there is a causal relationship, you have a strong positive relationship between hot chocolate sales and small marshmallow sales may be linked, right? Because when they sell more hot chocolate, you're going to include more small marshmallows in that hot chocolate. So these are more directly linked, and you would argue that there's a causal relationship. Finding relationships with the help of the correlation coefficient is a very good way to notice whether there's a connection, but it does not tell you whether that relationship is causal or next. What you would really have to do is usually carefully design an experiment that isolates and precisely controls only one of the variables to determine whether it's a causal relationship, if you can't do so just by your knowledge and context of the problem. That is it. You want to go ahead and try the homework where it's going to give you a number of additional examples to look at. Also, I would like you to try your best at the cool down activity on Google Classroom. Thank you.